Okay, I put some of you as a host also to add the others. Okay, now I think people came back, right? So please add them. I put some of you are admin or hosts. Okay. So what we said that now, if we want to simplify the circuit to the minimum gates, we are doing this basically for many reasons. First of all, to reduce the power consumption, to reduce the complexity also of that circuits. Okay, so if we have this example here, this example, and we say that please simplify it. Simplify it means just what you have to do. You have to remove these brackets. You have to remove if there is any complements. You have to remove. I mean, just to reduce the functions, instead of having, for example, here x and then x prime plus and then ORing. Look here, it's ANDing basically. This is ANDed with all these terms. So if we reduce these terms, these three terms, one term, then inside there are like two terms. If we reduce them to this value, it will be better. How we reduce it? This is mathematical manipulation. Just we will multiply the x into x prime, and from this part we will get 0, and then we will multiply x into xy, which will give me xxy, or it is xy as we explained before. X into x, it's equal x not x squared, and x plus x, it's equal x not 2x. Okay. Similarly, if you go for the second example here, you will find the same thing. If you have x, y, you hear us? You hear me? Hello?
Yes, sir.
Okay.
Yes, sir.
If you have x into xy, then you OR it. This is ANDing between them. Now again ORing here, again ANDing, again ORing, and you means you have a little bit. If we take it into the circuit level, it's a little bit complex. So what we are going to do, just we have to, for example, multiply them and to manipulate them in simple way of mathematics according to the postulates which it is with us, and according to the theorems which it's available there. So xy here, it's as it is. This is now x prime z. Then x y z plus x prime y z. So these things, like we are adding things, I mean, from our side, just which will not affect the things. So here here y z, if we multiply, I mean, just like we are multiplying these parts with x and x prime, means that in other words, this y z basically it is multiplied by x plus x prime. So just when you append x and x prime with it, you will get the same result. Now here from the theorems and postulates that 1 plus z or 1 plus x, this is ORing. 1 plus something, it will give you 1. The result is 1. So this is a type of rule. Here you are going to use it in future. Again here, 1 plus y, it will give you 1. So you'll be remained with xy plus x prime y. So the result of these, both of them, what will give you xy plus x prime y, x prime and z. So the result will be simplified. Now, complement of functions according to the De Morgan's theorems. If you have, for example, what we said, you have, for example, this type of simple circuits, Boolean function, A, you OR it with B, you OR it with C, or A plus B plus C. First of all, you have to take their complements. This is De Morgan theorems. First of all, you will take the complements for that. Second of that, you will convert the the ORing gate to ANDing. Means you are going to change the addition to multiplication. Okay, so this is in a very simple way, and this result here, it will give you different similar to the duality and the literal implements. So in literal and in duality, you are going to do the same step. Just you will these two steps, you will shuffle them. For example, first of all, you will take the complement, you will change the OR gate to be ANDing gate. Then from ANDing gate, you have to take the complements. These things you will find it all the time front of you during your this course and during your designing, and you will use it for many times. Look, now we are talking about the midterm and high term. This is now when we come. The first one, it was, look, it was the De Morgan's, then duality. Now the canonical forms for Boolean functions, it has two types: min terms and max terms. In min terms, only just I have to add the results so that I can get one at the end. If the function, if the expression with me, it have a value 1, then I say it's min term, and it has a timetable, it has a level that is moving through. For example, look here, I have A, B, and C, 3 inputs. Let me see these 3 inputs, and 0, 0, 0, it's represent 0 in decimal number, from in octal, or from 0 to 7. So front of each of them, I have to number it. So this level, it's equal M0. This level is equal M1, M2, M3, M4, M5 until M7. But what I mean by my term and by min term, until now I did not explain this. Just until now I have said that, okay, I have 3 inputs. These 3 inputs having different combinations, which they are equal to the from 0 to 7, and it is numbered basically, okay, front of all of them. Then each number of them, they have a value M0, M1, M2 until M7. Now I have to get my results. To make the first one 0, 0, 0, it's equal to M. Okay, what I will do in this case, to make this, just I have to invert the values. I will invert A, so it will be A prime, B, it will be B prime, C, it will be C prime. So in A, it's 0. The A complement for it, how much it is? It's 1. Then again, B, what is the complements for B? The complements for B, it is basically from 0 to 1. Then again, C, what will be the result? It will be 1. So when I take ANDing gates for them, it will give me 1. This only M0, I can say that M0, it is the A prime, B prime, C prime in min term. Similarly, if I go now for the others, so complement each element in each row from 0. If this, for example, 0, you have to complement it and make it 1. Similarly here, for example, if you see in the second line here, in the second line, no need to make the complements of C, because already C is 1. Only just I will complement these numbers. I don't know if you understand me or not. Are you with me, following me or not? Hello? 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 Arafah? Wasiq? I will take the attendance for you, you know? Hello?
Yes, sir.
Yeah. Hello?
सर आप बार बार म्यूट कर रहे हैं मैं.
Hello.
So all of you are hearing my voice, right?
Yes sir.
Okay. So again, did you hear anything about canonical forms or not? The explanation of this.
Yes, sir.
Okay. So did you understand what does it mean? Can mind terms here? Hello? Hello? Okay. You want me to re-explain it again?
Hello.
Hello? Yeah, yeah.
Yeah.
Sir.
सर ये
Yeah, yeah.
बार बार आप लगा देते हैं.
Unmute us sir permanently.
Sorry?
Unmute हो गए.
So I hear you. I hear you. Wasiq, I hear you. I hear all of you. Hello?
Yes, sir.
Yes. So so let's now continue. If you hear me, I will continue my explanation for this. Hello? Okay.
Yes, sir.
Okay, that's what. Okay, now look, again, I will explain to you the min term and max term. This was a type of revision, but it takes much time. Okay, anyhow, now for min term, we say that each zero from this, we have to convert it to be one. How to convert it to be one? We will take the implements, the complements for that. Okay, so to get to get the complement of these numbers, what we have to do, we have to take the x prime, y prime, and z prime. So just try to take the complements of each of these numbers and get your value. For example, if your value it's 1, it is 0 in a prime. In a, for example, here a, it's equal 0. What will be the result then? Just you will take the prime or the complement for that. B, again, you will take the complement. C, you will take the complement. Okay, so only in this stage, it will give you 1 when all of them are complemented. If I complement each row, okay, if I complement each of these primes here, okay, I mean, if I complement each number of these here, I will get the result of A prime, B prime, C prime, and which will give me M0. Again, because I got many like this term. Okay, so you have to do the things. Just you have to manage your time, your table for A, B, and C from 0 to 1. And this we know easily how to build it normally. Then we have to give it a sequence from 0 to 7. Then we have to give it a numbers from M0 until M7. Then we have to construct our mind term in just under one condition. We want all these values here should be 1. How to be 1? And this is ANDing process here between them, because in mind term I'm taking the product or AND function. So to make it AND function, to make them 1, so I have to convert each 0 here to be 1, each 0 here to be 1, and to convert this, so I have to take the complements. In the first row, they were all of them, they were 0, 0, 0, so it will be A prime, B prime, C prime. In the second one, now in the second one, it will be only the 2 first will be prime AB, and the C we are not going to do anything with it. The same thing if we come to the last one, all of them A 1 1 1. So I will not take any prime. So I am sure that the result of my term should be 1. Okay. So what about the max term? Have you understand this or not? Hello?
Yes, sir.
Okay.
Yes.
Okay. Now, what about the max term? The max term here, it is just, I will take the ORing function. ORing function means that I will do my level best to get a 0 result here. So this 0 result will be in max term because I'm taking the ORing. So for example, at the beginning, all of them, they are 0. No need to complement, to take the complement or inversion of any number. But at the end one here, 1 1 1, all of them, they should be complemented or should be inverted to 0 0 0. How? Just by taking A prime, B prime, C prime. Similarly, if I take, for example, this one here, this one 0 already there, this is 0 already there, while the C1, which I will take it as C prime. Okay. If I come to M5, for example, this one I have to convert it to 0. This is already 0. No need to take the prime for it. Now this one, I will take also the complement or the prime. So complement each element in each row 1 to be 0. Now the truth table, from truth table, when I want to build my Boolean function, just give me like 3-4 minutes, I mean, to go through all this and finish it. Then if you have any questions, we will explain it again in more details. So let's see here. This is the truth table. From this truth table, how can I make a Boolean function can be expressed algebraically from a given truth table by forming a min term for each combination of the variables that produce 1 in the function, and then taking the ORing of all of them. So at the beginning, I will see which one of these, this is F. F means the output or the Boolean function, the output of these 3 numbers. So this one here, it give me 1, means that there was like here, min term is going on. How? I have to convert this to 1. I have to convert this to 1 because I'm using ANDing gate, and I have, this is already 1. So what will be the result here? It will be like A prime, B prime, and 1, which is C without any complement. The second one here, if I come to this one. This one is 1 0 0. So what I will do in this case, just I will 1, it's already A, means no need to take the prime. I will take the primes of the 2 others and I will OR them. So here is ANDing going on, here is ANDing going on between them all. So come to this one. This will be A, B prime, C. Okay, now come for the last one. The last one will be A, B, C. Here is just how to, from the truth table, you can build or you can make your Boolean functions. Boolean functions, we say that if F has a value at the end of it, this value, if it is 1, so that I'm talking about the min term. If it is 0, if it is 1, like this one. If it is 1 here, so I am talking about the min term. If it is 0, if it is 1, I'm talking about and min term. If it is 0, I'm talking about OR function and 0 result. So now look again here. When I sum all of these, according, I have 2 ways for summing the functions. You remember? Before it was De Morgan, and the other one was what was that? The duality also, right? To convert them then to from and to or and so on. Now, if you can see here, A prime, B prime, C. Again, here I told you, look, these tables are very important. A prime, B prime, C. What is the value in M? it's equal M1, right? You are with me, right?
Yes, sir.
Okay, so
Yes, sir.
each number from these numbers, each number from these, just I will give it its value. For example, A, B, C, its value is M7. If I take 5, number 5, A, B prime, C, this is equal M5. Similar way, I'm going to use it here. After finishing these things, I will say that this one, A prime, B prime, C, it's available in the truth table, equivalent to M1. The second one here, A, B prime, C prime, it's equal M4, and so on. So the summation of these, only just these numbers, 1, 4, 5, 7. I can say that the Boolean function is equal to this. So if I have a Boolean function with this value only, I can construct this value, then I can construct the Boolean function, the mathematical expression for it, then I can construct the truth table, then I can construct my circuit design. You understand the things, right? If you have a circuit design, you can get the values from it. You will take the inputs, then you will take the outputs. You will see either it is AND or whatever gate they used, and you will go through it and you will build it. Then from that mathematical expressions or Boolean expressions, you can just give it their numbers according to the timetable. Okay, A prime, B prime, C means it's equal M1. Okay, if I say A, B, C means it's equal MF. This is in min term. In max term, it is only the same thing. I'm going to use the same process here. Only what I will do, I will take the complement first of all these values, the same one. If you can see, this is up, same thing. I will take the complements for them, and at the end of the day, I will just convert the dot product to the sum product to dot product. In other ways, in other meaning, if I take the complement of min term, I will get the max term. So this is available here. The complement of min term, it's equal to max term. How? For example, let's come to this example. If you have M, it's equal 1, 0, 1, which is equal M5. Means that M5 here is equal 1, 0, 1, which is equal A prime plus B plus C. Okay, this is in max term. Come here, 1, 0, 1. It's equal M5. It will be A into B prime C. Only just I took the complements because this was at that time, it was not complemented, while this one, A and C, they were complemented. Look, this one and this one was complemented. So when I took the complement of complement, will give me the original number, original element. While B was not complemented, now here, while B there was complemented, here it's not complemented. So now look here, for example, if you take, for example, here the sum products, we say that just now when we transfer this, now we take first, we have the values here of Boolean function, we take the complements for that, then complements of complements, just we remove them, then we got the products of these elements. At the end of the day, I have to take from these, I will take between these, there is ANDing, so I have to transform them to OR gates. So instead of dot here, it will be plus, instead of dot here, it will be plus. While this one, this here, the ANDing gate here, now it will just show me the beginning at the end of this one. Now just take now the other one here, the ORing between them, the ANDing between them, and convert it, transform it to the ORing level, and so on. So now A plus B plus C, it's equal M0 in max term. And this one, it can be seen from here. You remember, If you take this is a min term, this will be the max term. This here, the result of M0, M1, M2, M3, M4, M5, M6, M7. So, but here we are not representing the M's, because M's we know that, I mean the locations of them. The locations of them only. Just for example, here M1, it has been represented by 1. Here M4, it has been represented by 4. Here M5 represented by 5. Here M7 represented by 7. This one. If I take the complement of these, I will get the max term. This was the min term. Okay. If I take the complement of them, then I will take the max term. The max term means just I will invert. This one will be 0. This one will be 1. So here now the max term will occur where min term is not available. You got the point? I mean the complement of that we are taking only. So at the end of the day, the summation of max term is this one. The min term is this one, and the summation of max term is this one: 0, 2, 3, 6 from here. 0, 2, 3, and 6. So let's now talk about the standard forms which are used in canonical forms. One of them is sum of the product. If I have this, for example, Boolean function, then from this one, I have to just, for example, I will take the common between them, the common between these two elements. This sum product and product of sum basically used to simplify, as I said, the circuit and reduce the power consumptions, because you know in transistor or in microprocessor of computer we need like millions of transistors and gates are using theirs. Okay, so we have to reduce the power consumptions and the delay propagation from the input to the output. So here now, if we have these, if I take the common between them, I will be remained with C complement and C. C complement and C, it's equal basically 0. It's equal 1 from the postulates and theorems which we have seen it before. Again, if you take this one and take also the common between them, you'll get A prime plus B, and you'll get this result. If you take C, the other one, AC as a common, you will be remained with B prime plus B, and this is the result. At the end of the day, you will get this one again, this one. It will be ones, and you will be, now you have simplified your circuit from that type of inputs, all these complex circuit, and which it will use a lot of powers during the designing of your system, and you will be used only with a small function. Now, product of sum, it will be like this. For example, you will take again the common terms between them. You will take again the common terms between these. You will take again the common term between. So when you add them together here, again, these terms are ones, and you will get the same result here. At the end of the day, you will also complement all the results. So it is complemented here. Then you will take again the complemented results, which will give you this value. So now let's again talk, for example, here the standard forms. Here we can say that sum of min terms and products of max terms are almost minimized because each term contains by constructions all the variables are available there. So sum of product, in simple way, we can say that we have OR gate which add the ANDing gate. So we sum the ANDing. While product of sum, no, we product the OR gates. This is in a simple way. Okay. Let's see, for example, two levels of implementations. Now, if we have two levels of implementations, one is this one, which it is sum of product. So this here sum, and we OR all these functions. And here we have product of sum. Okay, this is a product. And here we have these functions are the sums. So we product all of them. So this is the type of the difference in circuit implementation between sum product and product of sum. So in three level, now we have, for example, three level of implementations. Hello?
Yes, sir.
Yes, sir.
Yeah.
Okay.
Are you with me?
Yes, sir.
Okay. One of you, as I told you that Rafa, you will take the, please, you will write for me the names, okay, at the end of the class. Okay, 3 levels. 3 levels, for example, here means that I have a circuit which it has 3 levels: ANDing here, then ANDing and ORing. So if you see it, it's like A, B, and C. I mean, many terms are available there and many processes also. For example, before I do the sum, I have to make a product. I have to make a product of sum here. I have to make, for example, this circuit, this is sum, then I have to put it here. Then I mean, it will be like 3 levels: 1, 2, 3. It will make the circuit more difficult for me, even not more difficult. It makes the circuit for me more consume for the power. So for that, what I will do, just if I take it now, this here F3, when I implement it like that, you know, C into D and C. But I can convert these 3 levels to 2 levels. Just what I will do, I open the brackets, this one. So I will use it and I will make it now. And I say that it is now some of the products and it's totally 2 levels. It's ORing here and ANDing here. No need to make ORing, ANDing, then ANDing with then ORing with some external values. I mean ORing, ANDing with other values. Then again, this result I have to take it to AND it with another results to make ORing for them. So many levels there. No, I just make it simple and easy. So now come here for the things. Since the beginning of the class, we are talking about the lecture, we are talking about the logical operators. And operator, it is XY. When we multiply both of them, it will give me a 0 in all cases, except when the 2 switches are on or when it is 1, 1. These 2 inputs, when they are 1, 1, it will give me 1. What about NAND gate? NAND gate means just I will add this inversion, this small inverter here, which will give me the opposite results for the previous one. So like I'm taking the complement, you know, like taking the complement values for that. So come to the ORing gate. ORing, it will give me all of it. It will give me 1, except when the both switches are off. Okay. So not or NOR gate, just I give it here a small inverter, which will give me the inversion or complement for the output result of OR gate. So now here it will be all of it are 0 except at this at the beginning. So XOR or exclusive OR gate. Exclusive OR gate, basically, whenever they are similar values, I have to give it, you know, this the difference between it and the OR gate. But the main thing is that here, whenever they have similar value, means that it is 0. Whenever they have a different values, this X and Y. X and Y, when they have different values, it will give me 1, 1. For XNOR gate, it will be the inversion for that. Whenever they have a similar value, they will be 1. Whenever they don't have a similar value, it will be 0. And these are the equations. Whenever you see them in front of you, I mean, in the next chapters, you are going to use it, because we are going next time to explain the 3rd chapter, which is gate level minimization, which we have to reduce the time of gates and level and operators to the minimum level, so that we make our circuits optimum and we reduce the power consumptions in the computers and the microprocessors. Okay, and all the integrated circuits. So inverter, this is the inverter. Whenever you have input, you will get the opposite result. Just you have to give, basically it is a buffer with only this one, with the inverter. So buffer is same, copying the results. So here some types also of the powers of the logical operators also. You can now go through all of them, and already we explained all of these together. So okay, today we will stop here, and inshallah next time just I will give you the remaining of this chapter, which about the integrated circuits. So we have to design the digital circuits using either hardware HDL or hardware implementations in the lab. In the lab, maybe have you taken any lab until now or not? Hello?
One lab.
One
Sir,
lab.
only one.
Okay, one lab. So in the lab, basically you were using these types of circuits, right? So that just what I mean that the circuits which we have know about it, the ANDing, ORing, and how to sum it and how all to use it, you have to implement it basically in these type of boards in the lab. So in market, when you go, I mean, or in future, if you are going to be, I mean, professional in this field, or if you go for advanced study of these courses, just you will fabricate what you have learned in the lab to make it these types of chips. Okay, so these chips, like the microprocessor of computers, like chip designs, like all these types of circuits, small circuits will be used there. So the chips basically is a die of silicon and semiconductors, and this which we said that we are going to study all these things, levels of integrations, which it is here again also the small scale of integrations. Small scale of integrations means that the devices which use like 10 gates. Medium scale integrations means that some devices using 1,000 gates. And this is are very small things. Like large scale integrations means that you are going to use like more than 10,000 gates. And these you are going to study it in chapter 2, chapter 4, chapter 6, and chapter 7. While the VLSI, which it is used like million, maybe more than million or million gates, something like this, which you use in microprocessor of the computers, the small computers. You are using more than million gates in that. And for all of that, what you have learned before, just to try to minimize your gates to reduce the power and the time propagation between the input from you when you switch your device or give the command enter until the output. So next time we will explain the rest 4 slides. Okay, and just let me take the attendance, please. Next time we'll go for third chapter. Okay. Third chapter, and just we'll give this one like 2 or 3 I mean minutes for the rest. Okay. So please, can we take the attendance? Have you write the attendance, Arfa?
Yes, sir.
You wrote all the names?
Yes, sir.
Okay, then
I
please.
wrote up.
Then please, you just make screenshot and send me on my WhatsApp. Okay.
Okay, sir.
Thank you so much.
Thank you.
Thank you so much for that. I hope that if we are in the class, it will be next time. It will be more better. I mean, and okay. What about your next your quiz? When you want the quiz will be?
After 1 week.
Okay, after 1 week means today is Thursday. So on Thursday will be the quiz.
Everyone.
Okay. So okay. What about the assignment? Because we have to make one assignment. Okay, the assignment you can do just to solve the problems of end problems of chapter 1 and chapter 2. Okay. Is it okay? And
Sorry?
from
There are all the problems.
it's not much. They are not much. Is there much?
Sir, 50 problems.
So sorry?
50 problems.
There are 50 problems. Okay, try with it. Try with it.
50 plus.
I think it's not much, and also it's, you know, you can say that it's not that much.
50 is not much. 50 is not much. Kya ho gaya?
Okay, then solve the first.
Half and three, sir.
Okay, solve the first, for example, the first 20 in each chapter, 40.